So in this video, we want to talk about how we can diagnose unusual values in the x-axis, or what we would refer to as leverage in our regression model. So identifying points of leverage, or levers, right, is based on how far individual data points deviate around from the mean on the x-axis. And we have to take into account the deviation of individual data points weighed against the overall deviation in our data. Because if we have data that are highly variable, then having one large variation doesn't seem unusual, right, when all the data are variable. But if all the other data are tightly clustered together and there's only one data point that is very far away and very different, that data is going to create what we would call a lever. And that lever, much like any sort of mechanical lever, can exert influence and change our model. So this really is meant to invoke the metaphor of someone pulling on like a pry bar, levering something up, because the farther away that data point is, the longer the lever, and then the easier it's going to be for that lever to change your model. So the book presents an example of this where we had hypothetical SAT verbal data and high school rankings for a series of high schoolers. And one set of data points got switched. So this person actually had their high school rank entered where their SAT verbal score should have been, and this person had their and then vice versa. Their SAT verbal score was entered where their high school rank should have been. So that creates a distribution of data that looks something like this. So we have this cloud of data points from everyone else that's in a pretty similar region, but now this person has a very different x-axis value, right? They have a rank of 48, but a much higher SAT value, right? Because this was actually their rank. And so now you can see that data point is up here on an island all by itself. And here we can see a line of best fit where the overall slope is negative, and both the slope and the intercept are statistically significant in this model. But we can see that this large data point out here in the upper left is ultimately driving this model down to give us a negative slope. And if we compare it against what the data actually look like, if we had corrected that, you can see now the data tell a very different story. For one thing, the scales on both the y and the x-axis are now greatly reduced because SAT scores and high school ranks are not exactly in the same scale, right? So making that transposition really change the scale of x and y. And now the slope is actually positive. And now actually it's statistically significant in the positive direction as opposed to being statistically significant in the negative direction. So simply having a type error in this one data point totally changed the interpretation of our model. And if we were just looking at the regression output, looking at the slopes and their statistical significance, we would never actually notice that one of these data points seemed a little strange, or that it seemed very far out of place, right? Because here in this situation, when we have the corrected values, that data point doesn't look statistically unusual. When we have this situation with those transposed values, that data point is actually generating a long lever arm because it's a very far away from all the other x values, and it is significantly influencing our model because it not only changes the sign of the slope, but it also changes its statistical significance. So we go from a positive statistically significant slope to a very negative statistically significant slope. So how can we identify these levers mathematically, right? Because we can look at these things on a graph and say, well, that one data point looks far away, but how far away is too far? So we can actually calculate a statistic known as leverage. And so the formula for the regression slope, as you might recall from previous lectures, right? Beta or B1 is our estimate of beta 1. So this is the regression slope in our sample, and it's based on the sum of the weights multiplied by deviations around the y-axis divided by deviations around the x-axis. And those weights are critically based on x. So the actual weights are x minus the average x squared over the sum of all the x's minus the average x squared. So what that is in essence saying, right, is for each individual data point, we're going to get a weight, which is based on how far that data point is away from the mean x. But that is balanced against how far away all these data points are on average against the mean x. So in this case, we have one data point that is very far away from the average x value, whereas all these other data points are going to have, reasonably similar distances to x. So for this one data point up here in the upper left, x minus x bar is going to be pretty large relative to the sum of all the other x's. Whereas for these individual data points down here, their x minus x bar is going to look a lot smaller compared to the sum of all the other x's. So this shows you how leverage is determined not just by the one individual data point, but also by the relative distance of all of the other data points. If I have a big deviation in a field of big deviations, it doesn't look as big. But in this case, I have a big deviation in a field of relatively small deviations, and that means that this lever has the chance to significantly influence my overall model. So the magnitude of the lever is referred to as h. So we have h sub I because each data point has its own h value. Now the letter h is used to represent the lever historically because the lever is also the diagonal of the hat matrix. And exactly what that means is a bit beyond our scope, but the hat matrix is a matrix that comprises the actual values of y, right, and the predicted values, or what we would call y hats. So that's why it's a hat matrix, and that's why we use h for lever instead of something like L. But as long as you know that h represents the lever magnitude. And when there's only one predictor variable, we can solve for this relatively easy. And the lever can be calculated as h sub I is equal to 1 over n plus that same weight term from our slope model. So we're looking at the individual deviation in x minus the average x, divided by the sum of all of the squared deviations in x, the sum of all of the deviations in x minus the average x. So when we calculate those weights, right, there are a few things that are important to remember. The first is that, as shown in the numerator here, the more unusual the x value, the greater the influence the data point will have on the statistics that we're trying to calculate. Now, this can be attenuated by having more data, right, which is represented by the n in the equation here. Because if we have an awful lot of data points, we're going to need a lot more leverage in order to have the same effect, right? But for a relatively small data set, a big difference in x is going to have a lot of influence. So then this changes then depending on the number of data points that we have, what the individual deviation is, and how big that individual deviation is relative to all of the deviations in x together. So specifically in terms of what we're looking for in these h values is we generally want to see if h is greater than p divided by n, where p is the number of parameters being estimated in the model, and n is the number of observations. So we will always have kind of a unique critical h value that we want to look at, but this would be the way you calculate that. And you could certainly have x values that have a higher leverage than your critical value. It doesn't necessarily mean that you want to remove them, but it does mean you want to take a look at those x values and try to understand where they're coming from and why they might have greater leverage. Was it an error, like we saw in this case, in which case we need to go back in and fit that error? Is it a physically impossible value, in which case we might want to exclude it? Or is there actually genuinely something about that person that puts them over here in this category? And then in which case your data might be real, but they might not really belong in the same sample with everyone else that you're trying to model. So this isn't necessarily grounds for exclusion in and of itself, but having those large lever values means we do want to take another look at our data and try to understand why we have that increased variability in the x-axis. So we want to check that, though, because ideally we want a model that accurately represents all of the data. If leverage is high, that means that one data point is having disproportionate influence in our model, or at least has the potential to have disproportionate influence on our model. And if our model is being driven by a single observation, that's clearly inconsistent with the goal of having the model describe all of the data. Right? So like I said, we don't necessarily remove a data point just because it has high leverage, but we do want to go in and check why the leverage for that particular data point is so high. And that involves asking more questions of our data before we make the decision whether or not that data point deserves to be excluded.